Okay, so 3.7, optimization. This is probably one of my favorite topics in calculus. So it's these are mostly applications, right? So these are applications to everything we've done so far in this chapter. Well, actually, everything we've done so far in this course, um, right? And so these are going to be the usual word problems. Um, and what I have is sort of a list of things to think about, right? These are guidelines. These are things that you should be thinking about when you're trying to solve these. Uh, Sometimes, like this example here, example one, it starts out very easy, but then they get more and more difficult as we go along. And so when they get more difficult, these are probably things you want to think about, right? So I'll just go through this list very, very quickly here. First thing you want to do is, of course, make sure you read the problem, make sure you understand it, and identify all the known or given quantities, and then the quantity that we're actually trying to find, and you're trying to optimize. So in some problems it might be to find the minimum, in other problems it might be to find the maximum. And in example one, of course, it says to find the minimum. So it's always going to be one or the other. In the questions, it's going to be clear whether you want a minimum or a maximum. So, right, so after you do that, then you write down what's called the primary equation. The primary equation is the equation that's going to involve the quantity that we want to maximize or minimize, right? So what quantities are we talking about here? Well, they could just be numbers, but these are physical quantities. It could be area or volume, right? So you might want to find the biggest volume or the smallest area, right? It could be a distance you want to maximize or minimize. And in somewhat more, financial applications, you might want to minimize the cost function, right? So you might want to minimize what your cost is. In other problems, you might want to maximize your revenue or your profits, right? So if you're running a business, you generally want to maximize your profits, right? So that's the idea of optimization, right? To maximize or minimize some quantity. All right. All right. So after you do that, what happens is that this equation, it might be a very complicated equation or it might be a simple one. But either way, it might be an equation that involves more than one variable, right? So more than one independent variable. And if that happens, we don't know how to maximize or minimize those. We need a function, excuse me. We need a function, say f of x, of some variable, right? We can't have a function of, let's say, x and z and r. We don't know how to deal with these, right? If you want to know how to deal with functions of more than one variable, you'll have to wait till calculus 3, multivariable calculus. So until we're able to deal with this, we have to reduce everything down to a function of one variable, right? And so that's going to be this step 3 here. Step 3, you're going to be reducing the primary equation to a function of one variable. And the way to do that, and again, that just doesn't make it clear, but the way to do that is to find a secondary equation that relates the two variables, or in this case, the three variables, right? So if we have, say, an equation or two that relates x and z and r, it could just be, it might be something like x plus z plus r equals 12, right? Or something that relates these three variables. Because once you do that, actually we need two equations here. So you might have another equation, a secondary equation, x minus 3r equals 0, or something like that. So once you have enough information, you can reduce this problem down to just one variable by eliminating the other variables. Okay, so maybe a bad example, but that's the idea here in step 3. Okay, step 4, you look at the primary equation. It's going to be a function at this point, like f of x, and you find the domain. Now, not just the domain looking at the function, but in terms of the parameters of the word problem. So for example, x might be some quantity. It might be a length, let's say. It might be the length of something, like the length of a fence. So what do we know about fences? Well, they have some length, right? They might be a very short fence like this, or it could be a very long fence, right? But it doesn't make sense to talk about a fence that has a length of, say, -2 feet. It doesn't make sense to be negative, right? So when you're talking about things like length, L for length, they're generally going to be positive, or at least equal to 0. So what would it mean if you have a fence of length 0? It just means you don't have a fence, right? There's nothing. So at least that makes some sense to say that you have a fence of length 0, but it doesn't make sense to have a fence of negative length. So it might not be apparent looking at the function, but your x might have to be positive as an example, right? So in other words, what makes sense for the problem, right? So if you're talking about length of a fence, you want your x or your L to be non-negative. And then finally in step 5, this is where the calculus part comes in. You take this function and you to find the minimum or maximum, what do? You need to find the critical numbers, right? So take the derivative, set it equal to 0, or find where it fails to exist. And those are your critical numbers, right? And typically you're just going to get one critical number. If you get more than one, you have to figure out which one's the maximum, which one's the minimum, and then, in this problem here, we want the minimum, right? So you can ignore any maximums, right? And then just make sure you answer whatever question they're asking here, right? All right, so that's what you should be thinking about when you're doing optimization problems, right? So now we get to our first example. Example 1, the problem is to find the minimum of the product of two numbers, one of which is 4 more than the other. Okay, so what are we looking for, right? We're looking for the product of two numbers, and we want to minimize that product, right? So what should our two numbers be? I don't know, how about x and y, right? So our two numbers are x and y. So the product of those two numbers, can I write P for product, is going to be x times y. Okay, so this is the quantity we want to minimize, right? Minimize this quantity here, right? This is what we're calling our primary equation. So in this case, P is not primary, P stands for product, but it fits both here, right? This is our primary equation. Okay, so how do you minimize something? Well, you take the derivative. But wait a minute, the derivative of what? With respect to what? X or y? See, this is going to be a function of both x and y, right? It depends on x and it depends on y. So we can't have that. We don't know how to take derivatives of that yet, right? So this is where step 3 comes into play. We need to reduce this down to a function of one variable, right? In other words, we need to reduce it down to, say, p of just x without a y. So how can we do that? Well, notice that we didn't really finish the problem yet. We didn't use this condition here. One of the two numbers is 4 more than the other, right? So what does that mean? Well, it means that one of these numbers, let's say y, is just going to be 4 more than the other number, x. So 4 more than the other number is just x plus 4, right? So x, that's the point. X and y are related, right? This is our secondary equation. It's an equation that relates the two variables, right? And so because of this statement, we can write down the secondary equation. Now, if y is equal to x plus 4, right, then I can replace y with the expression x plus 4. And so now I have our primary equation, but written as a single function, p of x. As a single variable, right? Only in terms of x. So this is our function, and it's a function of just x, right? And I don't know if you want, you don't have to, but we might as well expand this out. X times x is x squared plus 4 times x. Okay, so it's a quadratic function, right? So what do we want to do with this function? We want to minimize it. We want to find its minimum, right? Okay. Oh, I almost forgot step 4. What's the domain? Well, in this case, x and y are just numbers. They're just any two numbers. So I don't think it doesn't say positive numbers, doesn't say negative numbers. It could be anything. So I think in this case, this quadratic function has domain all real numbers. Okay, so there's really nothing we have to worry about the domain for this example here. All right, now how do we minimize this function? Well, we have to find the critical numbers. How do you find the critical numbers? Take the derivative, right? So whether you call it p prime of x or dp divided by dx. Again, I've been writing derivatives with the prime symbol for the longest time, so I think I'll continue to do that. Anyways, I'll give you 5 seconds to find the derivative. Hopefully you can do that by now. Yep, 2x plus 4. Nothing more to it than that, right? Power rule, sum rule, constant times function rule. Okay, all right, so how do you find the critical numbers? Well, you find where the derivative fails to exist. I think it's pretty clear it exists everywhere, right? All real numbers. So the only critical numbers here come from where this equals 0. And where does this equal 0? Well, negative 2. Negative 2. I'm distracted. I'm looking at this and I'm thinking maybe I messed up somewhere. One of which is 4 more than the other. Okay, I think this is correct, right? So this gives us a solution of x equals negative 2. Negative 2. So that's our critical number, right? That's our only critical number here. So if that's our only critical number, then this is probably where critical. This is probably the number we need. So let's answer the question, right? Find the minimum of the product of two numbers. Well, this is two numbers, right? What's the other number? If x is negative 2, how do you find y? Well, remember, y is just x plus 4. So x plus 4 in this case is negative 2 plus 4, which is positive 2. So there you go, right? X is 2 and y is, x is negative 2 and y is positive 2. And so what's the product? The product, right, x times y, negative 2 times 2 is negative 4. Right? So this should be the minimum product. Right? So does that make sense, right? If I take any two numbers, one of which is 4 more than the other, and I multiply those two numbers together, the smallest number I can get is negative 4 for that product, right? Right? I mean, you know, think I can pick any two numbers that satisfy this, right? I can pick x equals 0, and then y would be 4. But if I multiply those numbers, 0 times 4 is 0, and 0 is bigger than negative 4, so 0 could not be the minimum, right? You know, you can pick 3 and 7, right? X equals 3, y equals 7. And if you multiply those two numbers, 3 times 7, you get way bigger than negative 4, right? So, you know, I mean, again, I'm picking nice numbers, integers, but there's nothing here that says these two numbers can't be decimals or fractions, right? But I'm just picking easy numbers here. We could pick negative 3, and negative 3 plus 4 would be positive 1. So if I multiply x times y, negative 3 times 1, that product would be negative 3, which you notice is bigger than negative 4, but just barely, right? So yeah, I think any other pair of numbers that you pick, where one number is 4 more than the other, the product has to be bigger than or equal to negative 4, and it's only equal to negative 4 at these two specific values, negative 2 and positive 2. Sorry, it's a positive 2, right? So that answers the question, right? The minimum of the product of two numbers, the minimum is negative 4. Okay? So, right, so that's kind of an easy one to start. We'll do a harder one in just a second. Okay, so here's a second example from the same section. We have two adjacent rectangular pens, so these are the rectangles over here, right, are to be built with a total length of 60 meters of fencing. So this is where I got the fence example. So the total length of all, so we're looking from above here, right? So this is, we're looking down at the fence from above. Okay. And so this encloses some field inside the two fences, inside the fence, right? Two rectangular pieces here. Excuse me. We want to find the maximum area of the two rectangular pens. Sorry again. Right, so we want to maximize the area, right? We want to find the maximum area of these two rectangles. Okay. So I think the way to do that is, let's write down the area. Although I'll use the letter A for area here. So even though there's two rectangles, we want the maximum area of both of them, right? We want the total area. So the total area is just the length of this big rectangle here. The length is x, right? And the width is y. Okay? So this is actually not unlike the previous problem where we want to maximize the area, x times y. We want to find the maximum product of two numbers, x times y. The difference being that in the previous problem, this was a minimum. Now we want it to be a maximum. So it's a slightly different problem here, right? Okay, so again, the problem is that this is a function of two variables, x and y. So we don't know how to take derivatives of that. Right? So what do we need now? We need our secondary equation, right? Our secondary equation relates these two variables x and y. So what's the relationship? So if we read this carefully, we get a total length of all the fence of 60 meters. So if I add up the lengths of all 5 of these fences, right? The two ones lying this way horizontally and the other ones lying vertically, again, not vertical from the ground, but at least from the picture here, right? So in that sense, we have 2 of these horizontal pieces. So there's 2 x's, and then there's 1, 2, 3 y's. So this quantity here should be the total length of all the fence, of all these fences, all 5 pieces. And what do we know about the total length? Well, it's equal to 60. Right? So 2x plus 3y equals 60. This is the relationship between x and y, right? Between I've been calling this the horizontal and vertical piece, but I should call them the length and the width, right? So 2 lengths and 3 widths. How's that? 2 lengths and 3 widths, right? So that's our secondary equation. Right? This of course is our primary equation, a equals x times y. So so we do the same thing. We can eliminate one of the variables, either x or y. So I guess it depends. If you want this to be a function of x, as I think I would prefer in terms of x, although we could write this in terms of y. That's a bit unusual, but we can do it that way. So we do the opposite here. If you want this to be in terms of x, we're going to solve this for y here, right? So we get 3y is equal to 60 minus 2x, and then when you divide both sides by 3, you get that y is equal to 20 minus 2/3 times x. Okay, so now we have y in terms of x, right? But this y here is the same as this y here. So instead of x times y, it's now x times this quantity, 20 minus 2/3 x. Right? So this is now strictly a function of x. We have the area, and if all we know is the length, x, we can find the total area inside of these fences, the two rectangles here, right? Okay. So we can leave it like this, but remember, in the next step we're going to take the derivative. We want to find the critical numbers. So if you don't want to use the product rule, why don't we just multiply this out? This is just 20x minus 2/3 x squared, right? Again, you don't have to do it, but just like in the last problem here, we didn't have to multiply this out. We could have left it like that. But then when we took the derivative, we'd have to use the product rule. So to avoid the product rule, We'll just write it this way. All right, before we start, so going back to this, before we start finding the maximum minimum, don't forget we also want to find the domain. And in this case, this might be relevant here. X and Y can't be any numbers we want, right? For example, this is a length and a width. These aren't going to be negative. So I think we can say pretty definitively that X and Y are both positive numbers, or at the very least 0. Of course, if they're 0, you don't have a fence, you don't have an area. Right? So yeah, X and Y are both positive. Now, can X be, say, 100 feet, or 100 meters? Well, no, because you only have 60 meters to work with, and for not just for all these lengths and widths, right? So yeah, X obviously can't be bigger than 60, but even if Y were 0, you'd get 2X equals 60, right? So X would be 30 in that case, if Y is 0. So if Y is going to be bigger than 0, then X actually has to be less than 30. Or I'll say less than or equal to 30, right? So yes, if you shrink Y down to 0, you're increasing X up, so that it's 30. And because you have two lengths, you're going to get 30 plus 30 is 60. But then you're not going to have any widths, which means you don't have a rectangle. You just have these two horizontal pieces here, but you have no width. So you don't have a rectangle, right? So yes, our domain of this function, of the area, is we want X to be between 0 and 30. And again, I'll include 0 and 30 as possibilities, although as a practical matter, since you don't get an area here, it's really between 0 and 30. Yeah, and you don't get that by looking at the function here, because this is a quadratic function. The natural domain would be all real numbers. And that would be the case if this function were just out of the blue, right? If I give you this function and say ask the domain, you would say the domain is clearly all real numbers, right? However, this function comes from the physical problem. This is an area, right? And because it's an area, right, and X is a length, right, the domain is of the physical properties of this problem, right? So this 0 to 30 is not from just looking at the function. You have to look at the physical nature of this problem, and by looking at what happens when we shrink Y down to 0, we get sort of the maximum value of X, which is 30. Okay. Now, this really doesn't come into play in most cases, so I think I'm going way overboard in explaining this, but in some problems this might be necessary here, right? Just not in this one. All right, now comes the most important piece, right? The last part here, find the maximum and minimum. And so to do that, we find the critical numbers. So we take the derivative of A, or better yet, A prime of X. It's a prime, not a 1. And the derivative based on this is just 20 minus 4/3 X. Right? So, yep, the only critical numbers here come from where this equals 0. So you get 4/3 times X equals 20. So 20 times 3 is 60. And then when you divide by 4, you get 15. So this function here, let me make that clear, this function here, negative 2/3 X squared plus 20X, I'm just changing the order. We have one critical number, and it's X equals 15. Okay? Which, as you noticed, is right between 0 and 30. In this problem, that's not a coincidence. It's because it's a quadratic function. But don't expect your critical numbers to be exactly halfway between the endpoints of the domain. That just happens here. It's a quadratic function, so that's bound to happen. So, all right, so if X equals 15, we can find the maximum area. Well, first of all, how do we know it's a maximum? How do we know it's not a minimum, right? It's a critical number. It could be a maximum or a minimum. Well, we can use the first derivative test or use the second derivative test. Oh, Yep. Oh, I'm sorry. Yeah, so this was the original area. This is the derivative here. Sorry. So the second derivative will be 0 minus 4/3. So it'll be negative 4/3, right? And so when you plug in your critical number, you still just get negative 4/3. So what does it mean when the second derivative is negative? It means your graph is concave down. And when you look at the critical number at 15, right, tangent line is slope 0, so the derivative is 0 there, but because it's a maximum. So yep, that fits in the parameters of this problem. We are maximizing the area here, right? So what is the maximum area? Well, just plug in 15 into the original area function, right? So you get negative 2/3 times 15 squared plus 20 times 15. Oops, let me fix that. Sorry, it's the stylus. I call it a pen, but it's a stylus, right? So I'm just going to bring up a calculator here. So 15 squared is 225 divided by 3 times 2 is, so we get negative 150 plus 300, which I think is 150. 150 what though? So remember, x and y are in meters, so this is 150 square meters. Square meters. Or, you know, when you get to physics, you'll write it as 150 square meters. Either way is fine, right? So that should be our maximum area of these, the total area of these two rectangles. So by symmetry, of course, you can infer that since these two rectangles are equal here, that each one is 75 square meters because there's two rectangles. The 150 is the total of both rectangles. So I hope that helps. Of course, we never found out what y is, but we know y is 20 minus 2/3 x being 15 again, that's our critical number. So you're going to get 20 minus 2 times 5, which is 10. 20 minus 10, yep, is 10. Again, 10 meters, right? So this is 15 meters for x. So that's another way we could have found the area here. Remember, area is just x times y, x being 15 and y being 10. We get the same answer of 150 square meters. Oh, I forgot these are meters. So we could have gotten the answer that way too. Once you find x, you can find y using our secondary equation and then multiplying x times y to get the total area. Okay, so I hope that helps, and I think I'll leave it at that for the easy problems, easy optimization problems, right? One is just asking about numbers. It doesn't get easier than that. And then here you're asking about area. Of course, you should know area is length times width and things like that. You know, the area of a circle or things like that. Perimeter of a circle, perimeter of a rectangle. In this case, it wasn't just the perimeter, it was also the fence in the middle here. So I hope that's good enough.